So welcome everyone. Before I get started, I'd like to run a quick show of hands here, a quick poll. So who here uses Go on a daily basis? All right, nice. Who likes the concurrency model of Go? Everyone who doesn't know should put their hands up. Okay, who uses Scala native on a daily basis? One day, it'll come up. Okay, so today I'm going to talk about Scala's basic concurrency mechanisms and how we can leverage those to build a library, only a library, no language extension, that enables us to emulate Go's concurrency model. So what that means is having channels and lightweight threads that don't actually run on real physical processor threads. To get to that point, there's two concepts that are important, which is parallelism and concurrency. Often they're used interchangeably, but they actually refer to two different things. Parallelism is the concept of actually running a part of a program at the same time as running another part of the program, and concurrency is splitting up your program into parts that can then be run in parallel, but not necessarily in parallel, but you still get the same outcome regardless of what order you run them. So the premise of the talk is that I claim any scalable programs are going to need a good concurrency model at some point. By good, what I mean is a program that lets us be as efficient as possible, use modern hardware, so take advantage of parallelism, and also reduce the complexity in which we structure the program. That's also a very important point. To start out, there's one of the most basic concurrency abstractions, which is the thread. So a thread, as many people probably know, is a sequence of instructions. It has a single entry point, and it's a traditional way that's been used on operating systems for a while. Every thread has its own stack and kernel resources, so that means it's a fairly expensive resource. I mean, you can still on modern hardware run thousands of threads, but not millions. Oh, you're going to get in trouble. The other thing is every thread that runs on if a thread is running on a processor, gets taken off the processor, a new thread gets put in. That's also a fairly expensive operation, a context switch. But then the advantage, like I said, is threads are actually the unit that can be run on processors. It's like the native thing for the operating system. To illustrate this example here, we're going to look at the make meme method. It's going to follow us into many other concurrency models as well. This is on a single thread, the most straightforward thing you can imagine. What is a meme? It's an image superimposed by another image, which is the text on it. So if we, to create a meme, we need a URL and some witty text or something on it. This program here is, even someone who doesn't know Scala can very easily reason about it, right? We get the layer one, we fetch an image. So yeah, we just do the network call until we receive the result. The second layer of the image is we convert the text to an image, and then we superimpose things. So very straightforward. Anyone with any programming background is probably going to, in a reasonable amount of time, be able to determine what happens here. The unit of concurrency here is the single program. You can't run bits of the program in parallel. It's like you run the whole program, or well, you don't. There's no change in outcomes. The problem with running this not a problem, one of the shortcomings of running this as is that although it's very simple, it's very wasteful, right? Fetching a URL is we're sending off a network request, then we have nothing to do till we get the response back. Network request takes milliseconds if we're in a good spot. Processes in the order of gigahertz, so we're just like not doing anything. Sure, if your computer's running other programs, so if the unit of concurrency, you have others on the same level, then you're good. But usually, like if you have a server, this can become a bottleneck, or you're not taking as much advantage as you can. The other thing then is, of course, to get the result, you need the final result needs the result of two intermediate results. But you're only kicking off the second intermediate result once the first one is done. The classic example, well, the most straightforward improvement would be to just run these two in parallel. This is where multi-threading comes in. In like Scala pseudocode, it would look something like this. We define the results. We kick off two threads, run things in parallel. We need some synchronization. I'm like glossing over the details because that's actually one of the big difficulties in threads, making sure that your program is correct. Still looks straightforward. But so as I mentioned, is if you have multiple threads, to do anything useful in the end, you need some kind of synchronization, some kind of rendezvous, because otherwise the results are pretty useless. In hardware, that's typically implemented in hardware in very low-level instructions. But as a result, it means that reasoning about your program is much, much more complex, especially if you want to ensure that you're not going to run into deadlocks or any other kinds of issues. And then furthermore is that threads, even if they are blocked, so even if you're not running them because they're waiting on a network call, they're still consuming memory. We can say again, like, memory is cheap, just throw in some more RAM. Problem though is that we still have the issue of context switches if we are dealing with many threads. So what I'd say is, well, they're a low-level building block, but it's hard to use them as efficiently as possible. They're essential, but very hard to use right. Also, they're not available on any platform. Think of if you're using JavaScript, you get one thread. You can't run many things in parallel. So just to make that synchronization complexity a little bit better is oftentimes we structure programs, especially large programs, around queues. It enables us to decouple our logic. We have producers and consumers. I put something on the queue. Something happens. I don't care what happens with it. But you can model programs and reason about them fairly nicely with queues. This make meme model would look something like this. You see it's still very similar to the previous version, except we no longer need to deal with synchronization. The assumption here is that we built the queue that does synchronization correctly at put and take. So that means if I'm taking an operation, there is no operation, I'm just blocking. So the result of the program is the same. So what that gives us is we have a simple logic flow. However, we're still using exactly the same resources as threads. So if we step back a second and think of what does it mean actually that a thread is blocked, right? Like, what runs a thread? Well, that's the operating system. The operating system itself is just this big reactive state machine that takes input, does things like a timer, a network card interrupt. So what if we can, rather than trying to work on the abstraction of a thread, we try to take this callback, so this mechanism where we react on events, if we use that into our programs as well. So that's what callbacks are. A program with callbacks is typically can be seen as having many entry points. So you react really on methods. Typically how things happen if you don't have many entry points is when you start up, you register operations, so functions, or that's where the name comes back, callbacks, that should get run when an event happens. Typical examples, all of JavaScript, libuv, or any kind of event loop system, essentially. And in a sense, they are as fundamental, or sometimes you could say more fundamental than threads, because it's just action-reaction. Now, back to our example here. You'll notice that we're still doing the same thing, but the signature of the method has changed slightly. So rather than now returning a result, we are accepting an additional parameter, which will be called when the result is ready. Same goes with the fetch URL. We assume that this method now, rather than returning a result, also takes in a handler. And you'll notice that the logic is just extremely complex. For the simple thing we were doing before, all of a sudden we don't have this linear flow anymore to reason about what's happening, as we need to know the big picture of everything. We can't think about things in isolation anymore. It's much harder. Plus also there's an error. If we have, we can run into a deadlock issue here, or return 2 results if parallelism is greater than 1 here. So things like that you need to think about too. If we actually ran this, this is, I think, what we would get. Okay, so the advantages now of callbacks, though, are we never needed to allocate any additional memory for a thread. We don't need to allocate extra stacks. We didn't have any threads that would require context switch that needed to be taken off the processor and put back. So callbacks are very efficient. They don't have much resource overhead. They're available on any platform. Even if you have a single thread, you can have as many callbacks as you want. And finally, you can run them on many processors as well. The disadvantage, though, is we'll make things become extremely complex extremely quickly. And that's the name callback hell, if you've heard of that. So now, what if we could, rather than making callbacks work purely on side effects, so only registering changes, what if we could wrap them in a more functional way? So now we deal with transformations rather than side effects. All the time keeping the same characteristics. So the efficiency, but reducing the complexity. This is where Scala futures come in. You've probably seen these things. What they do is they wrap a single operation that eventually will return some result, some type. You can transform them with maps, flat maps, all the other goodies you have in collections. And when an operation is finally run, the future is going to one day complete either with a success or an error. If we look back at our program, this is how it has evolved now. So again, we're now returning a result, but rather than returning the actual result, we're wrapping it into a future. How we get the two images is, again, we assume these methods here would return futures to us. And then finally, the way we compose the result is with a simple for loop. And this is essentially just mapping over it. The for loop in Scala, in this case, is just a shorthand for running flat map, two flat maps on it. So program, again, looks much simpler. Still, I would say still not as simple, still a bit more complexity than the first single-threaded one, but at least we can distribute this on multiple threads. Now, though, you'll notice that I kind of said, like, oh, we assume we have this fetch URL and text to image. But at some point, futures, they don't just magically exist. We do need to interact with the environment. And since futures fundamentally wrap callbacks, at some point of this callback graph that futures are going to build, we need to interact with it. And this is where promises come in. So in Scala, promises can be sources of futures. So you can say, I create a promise, which just is this box where I can get a future of it, I can do my transformations on the future, and then at some point in a callback, for example, with my environment, I can imperatively complete the promise and then trigger this whole running of that blueprint that I constructed with the future. As an example, again, this would be in Scala.js. Assume we want to build a browser within a browser, because that's like what you do in JavaScript these days, right? So we need some way to get a URL from an input text box. This would be like our URL box. We would register here the callback, complete the promise, return the future, and how we actually use this is on the URL that we get, which is the future, we would map something that gets the URL, displays the website, and then again, to interact with the environment, one final callback handler. The thing, though, is we just have callbacks at the edges, not in between the operation. So now then the question, though, is how is it actually run the future? We could say that whoever completes the callback runs the entire graph. The problem, though, we don't really want to do that. Otherwise, we have these huge chunks of concurrency. Otherwise, we're, again, limited by how we can divide the program. So what we do is instead, the operation that every future, so every transformation on a future will itself become one of these chunks that gets scheduled on something called an execution context. So if you've used futures, you'll know for any operation on a future, you need an execution context passed as an implicit parameter. An example here would be, let's say we have some future, we flat map on it, we have another future, we map on it again. If we were to explicitly write execution context, you'll notice we need execution context for every operation on it, because these are going to be the cutting points to create these chunks that get put into the execution context. The execution context is then run on a thread pool. A thread pool is just a limited set of threads that have a work queue, so they will take these chunks, run them. When they're done, it's another callback, but this is all hidden from you to run the next element. And this is why you've probably heard that you should never block in futures, and this is precisely why, because if you do that, you're limiting or if you have a limited set of threads, you can just like run out of threads that you can do. Every other one is waiting. If you don't have a limited set, we're back to square one, what we said, where you're not taking advantage of resources efficiently. Okay, so then one so futures, are nice to use, but there's still a little bit of too much complexity in my opinion. That is, futures are hard to compose well. Let's take a little bit more of a complex example. We want to look up a user. This can be in a database, a network call, anything. And it might return a user or not. We don't know. So the result is a future of an optional user. We also have another method that for a given user and a set of capabilities can authorize it. Say, like, does this user have the authorization or not? What we return, though, is an option of user, because if we do not have the authorization, we don't want to reveal that. We want it to be transparent to anyone who calls us, like if the user exists or not, so they can't get any information out of it. If we want to combine these two methods, so to authorize a user by ID now, we run into something complex like this. You need to essentially, what you're trying to do is like map on the inner user. So you need to unroll the whole result set, do your transformation, and wrap it back up. And that can get much more complex if you're dealing with these very nested types. Of course, you can like restructure your program around it, but it's still just like it's fundamentally, they don't compose well. This is where you might have heard monad transformers. They can help you with that, but I still think they help you, but it's still an advanced concept. Someone who's totally new to the language, who comes away from an imperative background, looks at monad transformers and like, whoa, what is this? So they can help, but it's still not as simple as having this linear workflow. So all right, so the two shortcomings of futures would then be composition, as I mentioned, and the other thing is that futures are a one-time result. At some point they complete. It's not easy to model recurrent events. It's not a queue. It's just, it is going to happen or not. So the solution to the first shortcoming, that complexity of composition, can be solved with a library called scala-async. What it does is enables you to write code that looks synchronous, so back to that first example I showed, but actually doesn't use, actually can works with futures and can decompose these into, it has its own state machine which can then run these futures bit by bit, but the code that you see looks totally synchronous. I'll get to an example in a sec. It does this by offering two main constructs, which are async and await. You see async, the way it looks like is you put in some body that returns a result, but actually what you get is a future. Await that you can only use inside async, you can call it on any future and get back the result. This is again just syntax sugar, right? In the end, like there's no way you could do that without blocking. It's a macro that rewrites your code. It's also an official project from the Scala Center. That means it's not going to go away tomorrow. I'd highly recommend to check that out. It makes your code dramatically simpler if you have many nested future calls. This is how the program would look like. Essentially exactly the same as I showed in the first example, except that we now wrap things in an async block, and every layer gets this await in here. And so super simple logic again. Operations are kicked off in parallel, so we get all the advantages, but the logic flow for the programmer looks very linear, super easy. By the way, if you're familiar with futures in general in Scala, you might have seen the capital await. This is not the same thing, it's totally different. So capital await will block a thread, and they say that you should try to avoid using those, whereas these are it's just syntax sugar. Okay, so that solves the first shortcoming. There's still another shortcoming, though, which is that futures are a one-time value. They complete, but then that's it. You need to create a new future if you want a new result. So how could we work around that? Ideally, what we would want is something like queues and threads again, because this is how you model many interdependent interactions. The problem is, as we've seen, is traditional threads and queues, they block, and that's kind of what we've been trying to avoid all along. So this is where this project that I've been working on comes into play. The project is called Eskow, which means like a stop, because it's working like on a state machine that has many stops in it. It's inspired by Clojure's core.async library, which itself is inspired by scala-async, so we've come full circle. I highly recommend to watch Rich Hickey's presentation on it. It's excellent, explains all the advantages. There's also a talk about some implementation in it. So that's about the project. Now, what it actually does is it offers some extra constructs. There's something called a go, which creates like a coroutine. So it would run a block. Itself, it will return a future. I'm just showing these here for completeness. You're never going to need those. You have the concept of a channel, which is like a queue. You can put something into a queue, into a channel, and you can take something out of a channel. The definition, again, would have a future, but in the syntax, you will never see it. It will look totally blocking. Plus, there's some extra utilities like select, which is you can poll multiple channels, and you'll only get one result, one and only one, when it returns. It represents a form of communicating sequential processes, which means that there is a formal, if the implementation is correct, right? I'm not claiming that it is, but it would be nice. If it is, then that means you can reason about your program. You can actually reason, you can prove that it's not going to be blocking, things like that. Also, since we don't rely on threads, the runtime is totally abstracted. This can run on Scala.js, Scala native, and of course on the JVM. You can use as many threads as you like. This is how an example would look like. We have, of course, we need an implicit execution context, because that's what makes this whole thing work. Then we can declare, oops, sorry. We can create a new channel, give it the type. By default, channels have no size, so that means if you write to it, you're just going to block. I put block in quote marks because, again, you're not actually blocking the thread. If you arrive in that situation, your program is going to relinquish the thread is going to work on something different. And you can read from them. And the way you would start these asynchronous operations is with the Go construct. Again, Go is not starting a new thread, it's just giving you conceptually, it looks like it is. Another example is the select example here. So we declare 2 channels, and then we start 2 coroutines where we would write to both channels. The order here is not going to be guaranteed. So if I write this first, doesn't mean that this is actually going to happen first. It could happen that this thing here happens first. Again, these things, depending on your environment, can be executed in parallel or sequentially. But it's like totally abstracted from you. Then we can use the select call where we await one of the channels. And I mean, this is kind of a primitive, so only one will complete. You would never get both. This is a little bit of a primitive example, but this whole concept can be used to model things like sockets, web servers in this classic way where you would deal with threads and blocking, but you're actually not. The status of the project, it's still in kind of proof of concept. So what I showed you does work. I just want to write a README before I make it open source, but it has tests, just no README yet. It'll be available very soon. The channels are implemented, channels take care of buffering, so you can actually, rather than always blocking in a channel, you can give it a capacity, and the channel abstracts any kind of low-level locking if you do need to do some locking, because it could happen that you're actually running in parallel on multiple threads. As I mentioned, put and take, they actually return futures, so you can use them in non-Go code, so without that nice syntax sugar. Oh, by the way, so I should have mentioned this. This operation here is the same, so this means put. This is the same as calling channel2.put1, except it's syntax sugar that only works in the Go routine, because we're not returning a future anymore, we're actually returning the result. Same goes for the read. Yes, so what was I going to say? Yeah, so as I mentioned, put and take actually return futures, but there's syntax sugar on top of it. Same goes with select. It's a little bit more complex, but it's also just a future. And we're piggybacking on scala-async to create this illusion that we're dealing with synchronous code. And of course, yeah, there's a bunch of syntax sugar on top of it, so we can, so it just looks much nicer. The roadmap is, as I mentioned, it's a very early project, but there's some features, fundamental features that aren't yet implemented. One of them is we want to be able to close channels. We need to deal with error handling. I just showed you the happy path. Where the way we're using scala-async is generating futures and then relying on scala-async. So we have a macro that generates a macro that then gets expanded. So for proof of concept, it's fine, but ideally what we would want to do is hook into, so scala-async creates the state machine of your program graph, hook into that directly, right? Because we can't do that, we're a macro. But that would need a little bit more, I need to explore a bit more of how we can hook into that. Potentially, I've heard there's a project called Scala Coroutines that might be able to work in conjunction with this. Then some other features, like I want to be able to select on puts so that I can wait until one channel is available to write on it. Also supporting buffer policies. You don't always want to block on a buffer. Sometimes you can say like, oh, if I receive an extra result, drop the first one, drop the last one in my buffer. You never want to have an unlimited buffer because that's you're going to recipe to run out of memory. but some other kinds of policies are interesting. Of course, then some API improvements. So I would love to have an alternative to symbols. I modeled the symbols because I copied the Clojure async. Clojure async used essentially these same symbols, so I just like copied their convention, but I think put and take is clearer. Other thing is this wildcard. I'm not a fan of having these imports. It's just magic. I'd much rather import explicit things. Currently, it's not possible because we need an implicit that gives us some of the syntax sugar, but I'd like to see if there's not a way we can come up to model this differently. Finally, some refinements on types so we can pass channels as a read-only or write-only instance to other methods. So just to summarize here, what does this project do is we've replaced threads and queues with conceptually lightweight threads and queues. So programming model is again the same. So it's all about reducing the complexities. You can program with these familiar concepts, but you get better concurrency, much more fine-grained things. And the environment is going to take care of running it. You can run on Scala.js, any environment you want. And it's all done in the library. It's not in the language. So Go, for example, they designed the language so they could integrate this green thread, lightweight threading, channels, abstraction very nicely into the language. Scala fundamentally was developed to run on the JVM. The JVM uses threads. So we can't really build that into the language itself. So it's really nice that we have the power to do it in a library, though. And again, so to summarize, we've just added another layer of indirection. So you solve problems. Finally, I want to say there's, of course, other approaches to concurrency. There's, you might have heard of actors. Actors and communicating sequential processes are very similar. They are opposite in many ways, but that you can model the same things. Actors are named entities. You send messages to an actor, whereas processes, they are anonymous. You don't give a name to a Go process. So I just wrote Go. The message path, on the other hand, on an actor is anonymous. You don't say how a message is going to arrive to an actor. You actually send it to this to an actor. It just goes there. Whereas channels, again, they are, in this case, channels are named. You say, like, I'm writing to this channel. Sending messages is fundamentally non-blocking in actors. So actors have a mailbox. It's unlimited. You can keep sending them things. Whereas channels, they are have a bound buffer within them. That means you can use channels to serve as a synchronization point. You can actually make your code stop, or again, look like it stops, while you're awaiting a result. This makes logic, reasoning about things much easier. Of course, on actors, you can build that thing on top of it as well by creating these protocols saying, like, hey, I'm going to send you a message. If you have memory, respond, please. And you can emulate that on top of actors. This is kind of what reactive streams do, and any of these streaming library. There's this whole process of asking, like, hey, can I get new element? This whole protocol to get back pressure, whereas in channels, you have back pressure built in. Finally, this is quite an advanced and powerful concept. And in the spirit of keeping things simple, making it easier for other people to understand, because that's like the whole reason this library is built, is, well, first, if you can get away with it, just write a synchronous logic. That's the easiest you can do. Of course, many times, especially in server applications, you don't want that. In that case, futures and promises with scala-async are perfect. If you do need to then model recurrent events, I would suggest, well, you could give this project a try, or any of the other concurrency libraries. And finally, well, if you really, really, really have no choice, then you can consider callbacks. But those are like, don't try to avoid them. Thank you for listening. I will make the project open source very soon. If you want to check it out, I'd love to get more feedback on it. I think we have some time for questions. Yeah.
What is the approximate runtime overhead of this? If you had some of these full Go-like examples and you implemented it both in this system and in Go and then compiled to Scala native or by a Scala native to a native binary, what would you expect the performance of the system to be compared to?
Yeah. I think I don't know if my mic is working, so I'm going to take that. So from what I understood is, like, what would the performance comparison with Go be? It's a bit too early to say. It's really just a proof of concept. First of all, the compile time performance is presumably going to be pretty bad as it stands because I have this double macro expansion, right? But I can imagine the runtime itself is, I don't know. It would just run as fast as promises and futures, essentially. So I can't speak too much of it. But one of the key things is, I think to make this actually useful is we would need to, try to come up with a way to actually build libraries that kind of, use this. Maybe some networking libraries that try to take care of it, because this is just like as it is. It's nice, but
It's not practical use case. Yeah. Yeah.
I want the least amount of dependencies possible. I want something that just requires Scala, that when new version of Scala comes out, I can run this directly on it, or as soon as possible. Of course, yeah, you make a good point. Like, I didn't mention scala-async cats. There are like many frameworks that offer similar concepts, all these channels, right? But this should be a more low-level thing that can still model the communication.
So this is amazing, but like I'm trying to compare it with PyCalculus. In PyCalculus, there was a problem to pass a tuple through a channel so that the same agent, like if one agent sends a pair like A and B, so the receiver will receive both A and B and not like a couple of receivers. The solution was known as Odersky ziplock, so maybe you can comment how you can do it with your system.
I'm not entirely sure I understand. So what was the exact issue? If I'm sending a tuple over a channel?
There are like 5 senders, 5 receivers.
Yes.
There are 5 senders, 5 receivers. And if one sends 2 values, so we want the same 2 values, like another sends stuff too. So the same 2 values to be received by exactly one consumer. And not like spread around you do.
It's not built in, it's up to you to design. Yeah, so it's multiple readers, multiple writers. You write it, you don't know which writer's going to get it. It's like, there's no, you have to model that. It's very low level. Any further questions? All right, well, thank you.